Question 4.76. A ball having a mass of 1 kilogram is attached to a string 1 meter long and is whirled in a vertical circle at a constant speed of 10 meter per second. First part of the question is asking you to determine the tension in the string when the ball is at the top of the circle. So here in this question, you have a ball of mass m equals 1 kilogram that is whirled in a vertical circle with the help of a string 1 meter long. And the length of the string is also the radius of the circle. So we can write r to be equal to 1 meter. And the speed of the ball as it moves around the circle is constant, which is along the tangent to the circle at any point. And we will write the speed v as 10 meter per second. We need to find what is the tension in the string when the ball is at the top of the circle. So let us first show all the forces acting on the ball when it is at the top. The first force is the force due to gravity, which we will call Fg. And Fg is pointing vertically down. And then you have the tension in the string, which we will write as capital T. And the tension in the string always points towards the suspension point, which in this part of the question is pointing down. And since both of these forces are pointing towards the center of the circle, these are the forces that will provide the ball the required centripetal force to continue along the circular path. So I can write as my net force along the y-axis, because these two forces are along the y-axis, is providing us the centripetal force Fc needed to keep the ball in circular path. So the net force along y-axis is sum of the tension force and the force due to gravity. So we write T plus Fg is equal to Fc. All of these forces are pointing towards the center of the circle, which at this position is pointing down. Therefore, if I take negative sign for each of them, it will just cancel out. So I can ignore the negative sign for this particular position. Then we have to find the tension in the string, so we rearrange the term. I write T to be equal to Fc minus Fg. From the definition, centripetal force can be written as mv squared over r. Fg is the force due to gravity, which is m into g. So you can calculate T as, let's take m common, v squared over r minus g. Now let's substitute the values. Mass of the ball is 1 kilogram. Speed v is 10 meter per second, so 10 squared. The radius r is 1, minus g is 9.81. And when you solve this, you get the tension at the top of the string to be equal to 90.19 Newton, or you can round this off to 90.2 Newton. Next, in part B of the question, they want you to determine tension in the string when the ball is at the bottom of the circle. So again, first we will find out what are the forces acting on the ball at the bottom of the circle. First, you have the force due to gravity, which we will write as Fg, pointing vertically down. Then you have the tension in the string, which we will write as capital T, pointing towards the suspension point. So in this case here, towards the center of the circle, that is up. And as we can see from the figure, the net force resulting from these two forces is providing the ball the required centripetal force to continue in the circular path. So I can write the net force along the y-axis is giving the ball the required centripetal force Fc that will keep it along the circular path. So F net y we can write as T minus Fg, because T is pointing towards the center of the circle, which is in the upward direction in this position here. So T will be positive. Fg is pointing down, so it has to be negative, which is equal to Fc. Fc will be positive over here because centripetal force at any given position points towards the center of the circle. So if I draw a vector pointing towards the center of the circle at this position here, it is directed upward, which by convention has to be taken positive. So now rearrange to find T. I get T equals Fc plus Fg. Fc can be written as mv squared over r and Fg as m into g. Take m as common. V squared over r plus g. Now substitute. M is 1 kilogram. V is 10, so 10 squared. R is 1 meter plus G, which is 9.81. Now I already considered the negative sign of the G in the equation of net force, so you did not substitute this G as negative again. Solve and you get the tension in the string to be equal to 109.8 Newton. So this is the tension at the bottom of the string. Now let's consider part C. Part C of the question says, consider the ball at some point other than the top or bottom. What can you say about the tension in the string at this point? So let's take any point P between the top and bottom. And we need to comment about the tension in the string at this point P. Now for a vertical circle, tension in the string is maximum at the bottom. So I can write tension at the bottom of the circle to be having the maximum value, whereas tension at the top of the circle is minimum. So at any point P which lies between the top and the bottom, tension at point P will be intermediate between these values. That means it will be greater than tension at the top, but smaller than the tension at the bottom. So as you go from the bottom to the top, tension in the string will reduce and it will go from maximum value at the bottom to minimum at the top. And when you come from top to bottom, tension in the string will start to increase, where it will go from minimum at the top to maximum at the bottom. And at any point in between this position, the value of tension will vary in the manner shown here. It will be greater than the value at the top, but smaller than the value at the bottom.